Hello everyone, I am Nivedita Chena from Ambika Prasad Research Foundation. Welcome to all of you to our channel Biodiversity and Conservation. So today is the unit 1 part 4 of environmental science, in which we are going to discuss about the laws of thermodynamics. So in physics, thermodynamics is the study of energy conversion between heat and mechanical work, and subsequently the macroscopic variables such as temperature, volume, and pressure. The starting point for most thermodynamic considerations are the laws of thermodynamics, which postulate that energy can be exchanged between physical systems as heat or work. They also postulate the existence of a quantity named entropy, which can be defined for any isolated system that is in thermodynamic equilibrium. In thermodynamics, interactions between large ensembles of objects are categorized. Central to this are the concepts of system and surroundings. A system is composed of particles whose average motions define its properties, which in turn are related to one another through equations of state. Properties can be combined to express internal energy and thermodynamic potentials, which are uh, which are used which are useful for determining conditions for equilibrium and spontaneous processes. And here in this slide, we can see the typical thermodynamics engine with showing input from a heat source on the left and output to a heat sink, which is condenser on the right. And work is extracted in this case by a series of pistons. Then coming to laws of thermodynamics, the field of thermodynamics studies the behavior of energy flow in natural systems. From this study, a number of physical laws have been established. The zeroth law: if two thermodynamic systems are each in thermal equilibrium with a third, then they are in thermal equilibrium with each other. When two systems are put in contact with each other, there will be a next exchange of energy between them unless or until they are in thermal equilibrium. That is the state of having equal temperature. Although this concept of thermodynamics is fundamental, the need to state it explicitly was not widely perceived until the first third of the 20th century, long after the first three principles were already widely in use, hence it was number 0. Before the And the zeroth law asserts that thermal equilibrium, viewed as a binary relation, is a transitive relation, and since any system is always in equilibrium with itself, and if a system is in equilibrium with another, the latter is in equilibrium with the former, it is furthermore an equivalence relation. The first law of thermodynamics is energy can neither be created nor destroyed, it can only change forms. In any process in an isolated system, the total energy remains the same. And secondly, for a thermodynamic cycle, the net heat supplied to the system equals the net work done by the system. Uh, so simply, the first law states that energy cannot be created nor destroyed, or rather the amount of energy lost in a steady state process cannot be greater than the amount of energy gained. This is the statement of conservation of energy for a thermodynamic system. It refers to the two ways that a closed system transfers energy to and from its surroundings by the process of heating or cooling and the process of mechanical work. The rate of gain or loss in the stored energy of a system is determined by the rates of these two processes. In open systems, the flow of matter is another energy transfer mechanism, and extra terms must be included in the expression of the first law. Then the second law is the entropy of an isolated system consisting of two regions of space isolated from one another, each in thermodynamic equilibrium in itself, but not in equilibrium with each other. Well, when the isolation that separates the two regions is broken, so that the two regions become able to exchange matter energy, tend to increase over time, approaching a maximum value when the jointly communicating system reaches thermodynamic equilibrium. In a simple manner, the second law states energy systems have a tendency to increase their entropy rather than decrease it. This can also be stated as heat can spontaneously flow from a higher temperature region to a lower temperature region, but not the other way around. And heat can appear to flow from cold to hot. For example, uh, when a warm object is cooled in a refrigerator, but the transfer of energy is still from hot to cold, the heat from the object warms the surrounding air, which in turn heats and expands the refrigerant. The refrigerant is then compressed, expanding electrical energy. The entropy of an isolated macroscopic system never decreases. However, a microscopic system may exhibit fluctuations of entropy opposite to that stated by the system. So, the third law of thermodynamics is as a system approaches absolute zero, all processes cease, and the entropy of the system approaches a minimum value. If the entropy of each element in some crystalline state be taken as zero at the absolute zero of temperature, every substance has a finite positive entropy, but at the absolute zero of temperature, the entropy may become zero, and thus the become in the case of perfect crystalline substances. In simple terms, the third law states that the entropy of most pure substances approaches zero as the absolute temperature approaches zero. This law provides an absolute reference point for the determination of entropy. The entropy determined relative to this point is the absolute entropy. The tentative fourth law is over the years, various thermodynamic researchers have come forward to ascribe to uh, potential fourth laws of thermodynamics, either suggesting that a widely accepted principle should be called the fourth law or proposing entirely new laws. In some cases, even fifth or sixth laws of thermodynamics are proposed. The most fourth law statements, however, are speculative and controversial. The most commonly proposed fourth law is the uncycled reciprocal relations, which give a quantitative relation between the parameters of a system in which heat and matter are simultaneously flowing. So for this part, that's all about the thermodynamic laws. Thank you.